So let's get started. Today we are going to have lecture number 4, and it's going to be about the Cartesian vectors, and also we are going to learn how to add the Cartesian vectors. Like you can see here, we are going to face many structure and machine involve three-dimensional space, like this one. And we know that when it comes to 3D, it's going to be complicated. And in order to make it more convenient, we are going to use the Cartesian vectors. Of course, today we are going to explain how to deal with Cartesian vectors. And the reason for that, because the operation of vectors algebra, it's easy and it's greatly simplified. So in order to deal with 3D problems, we are going to use the Cartesian vectors because the operation of the vector algebra is easy to handle. First, in order to, to deal with Cartesian vectors, we need to have a coordinate system. For example, when we have 2D, we used to have X and Y, and it's very simple coordinate system. But in 3D, we need 3 dimension. We need to have X and Y and Z. And in order to know the positive and the negative, we need to use the right-handed coordinate system. So in how we are going to use the right-handed coordinate system. So this one, we need to use our right hand. And like you can see here, here is the right hand. And I need to put the thumb up in the positive direction of Z. So the thumb here indicates the positive direction of the Z, while the fingers here, the right fingers here, they are rotate about the axis Z, and it's directed from the positive X toward the positive Y. So the fingers here is going to direct from the positive X toward the positive Y. Here we have the positive Z, here we have the positive X, and here we have the positive Y. And that what we are going to use regarding the Cartesian vectors. For example, here, after we fix our coordinate system, now we have a vector in 3D. And we want to know the components of that vectors in X and Y and in Z. Previously, we deal with 2D situation. In 2D situation, in order to know the components of that vector here, we use the parallelogram law. But that was on 2D. Now we have 3D, and we need to know the resultant, the component of the vectors A here. So here we are going to use what we have studied in 2D regarding the parallelogram law. But this times, I'm going to do it in 2 steps. I'm going to apply the parallelogram law 2 times. First, since the vector is here, I'm going to assume that I'm dealing with X and Y. So I will assume this one is X and this one is Y. And I'm going to say this one is 2D plane here. So since I am going to imagine this is a 2D plane, I'm going to use the parallelogram law. I'm going to draw a parallel line here and parallel line there and connect them. Then I'm going to say that the vector A dash plus the AZ is going to give us the vector A. So we are going to say that A vector is going to equal A prime vector plus AZ vector. Then now I have the A prime vector here. Again, I'm going to say that I'm dealing with only 2D. This one is X and this one is Y. So I'm going to ignore everything. I'm going to know the component of the A prime here. So again, I'm going to apply the parallelogram law. I'm going to draw a parallel line here and parallel line there. And then I'm going to say that the vector of AX plus the vector of AY is going to give us the vector of A prime. Then we are going to say that A prime, in fact, equals the AX vector plus AY vector. And instead of A prime here, I'm going to put AX plus AY. So finally, we are going to say that the A vector in 3D is going to equal the vector of AX plus the vector of AY plus the vector of AZ. In 2D, we are going to say that A equal the vector of AX plus AY. But in 3D, we are going to have 3 components for that vector. And also in the Cartesian vectors, we are going to use the unit vectors. The unit vectors show us the direction of the component itself. So we have I, and we have J, and we have K. So we are going to use I to indicate that the direction of the force is in the positive X. And we use the J in order to indicate that the direction of the force is in the positive Y. And we use K in order to know the direction of the force in the Z direction, in the positive Z direction. And the sense of the vector here, like you can see, I have arrow here. This one indicates to the positive part. But if it was in that direction, that means the I is negative. So I, it could be positive or it could be negative. It depends on our coordinate system. In the beginning, we said that in this direction is going to be considered positive, which means that plus, we put plus here. If it was in the opposite direction to this one, then it's going to be minus. The same thing for J. If it was there, then it's going to be minus. And the same thing for the K. If it's in that direction, then it will going to be minus. So now we are able to describe the vector in 3D using the Cartesian vector. We know that the vector here is going to have 3 components. We are going to have components in X, and component in Y, and component in Z. And I'm going to put the I and the J and the K to show us the direction of the component. So we are going to say that the A vector is going to equal the AX magnitude it's mean that the component here is in the positive direction of X. Then plus AYJ. AY is the magnitude of the vector in the Y direction, and J indicates that is in the component is in the positive part of Y axis. And here we have plus AZK. AZ is the component of the vectors in the Z direction, and K is the unit vector that indicate that the component is in the positive part of Z axis. And you are going to ask yourself why we are using this formula. This formula here, we separate the magnitude from the direction. So this one is the magnitude, this one is the direction, magnitude, direction, magnitude, and direction. Because when we are going to make any operation of using vector algebra, using this formula make it very easy in order to add them or subtract them, like you are going to see later on when we are have more than one vectors and we want the resultant in 3D. Without using the Cartesian vector, in order to get the resultant for many forces, for here I have only one vector, maybe I'm going to have vector here and vector here, and if you are going to use scalar notation, it's going to be very difficult for us to handle it. But using the Cartesian vector is going to be very easy. So especially in 3 dimension, we are going to use the Cartesian vector. Also, in order to calculate the magnitude of the Cartesian vector, like you can see here, we have right angle here. So also we are going to use the cosine law, except that the angle here is 90 and cosine 90 is 0. Then that part where you have minus 2ab cosine, the opposite angle is going to gone because this one is 0. So here again, I'm going to deal with the problems into 2 parts. The first part here, I'm going to say that the magnitude of the vector A is going to equal the square root of A dash square plus AZ square. And then I'm going to know the magnitude of A dash. Again, here I have a 2D situation. I'm going to say that A dash is going to equal the square root of AX square. This one is AX square, and this one is AY square. And then instead of putting A dash, so here is A dash, the A dash square. When you square this part, then you are going to have AX squared plus AY squared. Then the magnitude of that vector is eventually going to equal square root of AX squared plus AY squared plus AZ squared. And this is how we are going to calculate the magnitude of the vector in 3D. In 2D, we used to say that A is going to equal the square root of AX squared plus AY squared. But here, since we are dealing with 3D dimension, we are going to have 3 components. And also we need to know the angles here. So we need to know the angles so that we can finish the Cartesian vectors. So we have 3 angles. We have alpha, we have beta, and we have gamma. Alpha is the angle between the vector A and the x-axis. And beta is the angle between the vector A and the y-axis, while alpha is the angle between vector A and the positive z-axis. And of course, if you think about it for a moment, you are going to figure this out. All these angles are between 0 and 180. Now we need to know how we can calculate these angles. Like you can see here, if you are going to take this triangle here, you are going to find this angle is the right angle, like this one. And the angle here is alpha. So we know that when we have right angle, we can say that the cosine of alpha equals the adjacent over the hypotenuse. So cosine alpha is going to equal AX over A. The same concept, it could be applied for beta. We can take this triangle here, and we are going to see this one is the right angle, and here we have a beta, and then cosine beta is going to equal the adjacent over the hypotenuse. The adjacent here is AY, and the hypotenuse is A. And similarly, we are going to apply the same concept for alpha. So here we have alpha, this one is the right angle, and cosine alpha is going to equal the adjacent over the hypotenuse. This one is the adjacent, and this one is the hypotenuse. I know that we have got a lot of information, but we are going to use all of them together, and it's going to be simplified for you. The last concept that we need to discuss is the unit vector. So when we define that, we can, if we are going to draw a vector like this one, so this one is vector A. And the length of that vector is the magnitude. If you have the vector and divided by its magnitude, we are going to have what's so-called unit vector, UA, U sub A. So U sub A is the vector over its magnitude. And the unit vectors is very important because we are going to use the unit vector in order to relate the relation between the position vector and the force vectors. Later on, we are going to use the concept of unit vector in order to move from position vector to force vector. Now, if the unit vector is going to equal the vector itself over its magnitude, that means the vector A is equal the magnitude dot the unit vector. And the magnitude of the unit vector is going to equal 1 because we divide the vector over its magnitude, over its length. And the unit vector, it's dimensionless, which means that it doesn't have any units. And always it's point to the same direction as the original vectors. So the unit vector is going to direct to the, or it's going to point to the same direction of the original vector. And the magnitude of the unit vector is 1, and it's dimensionless. Now, we said that the unit vector is going to equal the A vector over A. And we already said that in Cartesian vectors, A is AXI plus AYJ plus AZK. And if you are going to divide it over its magnitude, that means you are going to divide each terms over its magnitude. So here we are going to have AX over AI plus AY over AJ plus AZ over AK. So now we divided each term over its magnitude. And if you do remember here, when we define the angles, we say that cosine alpha is AX over A. And cosine beta is AY over A. And cosine gamma is AZ over A. So here we have AX over A. So instead of writing AX over A, I could write cosine alpha, because we said that cosine alpha is AX over A. And the same thing here, we have AY over A, we are going to write cosine beta. And instead of AZ over A, we are going to write cosine gamma. And since the magnitude of the unit vector here, remember we said that the magnitude is going to equal 1. That means cosine alpha I plus cosine beta j plus cosine alpha k is going to equal 1. And with using a small manipulation, we are going to find that cosine squared alpha plus cosine squared beta plus cosine squared gamma is going to equal 1. Now we finish from defining the Cartesian vectors. We have the vectors here. A is going to be represented by AXI plus AYJ plus AZK. And also I can calculate the magnitude. The magnitude is going to equal square root of AX squared plus AY squared plus AZ squared. And also we define the angles, the alpha and the beta and the gamma. And also we learn how to calculate the unit vector. The unit vectors is simply the vectors over its magnitude. So again, instead of using vector A, I can use, of course, vector F. The same concept. If I have vector F, then in order to present this as Cartesian vector, I'm going to say that F equal Fxi plus Fyj plus Fzk. Fx is the component in the x direction, Fy is the component in y direction, Fz is the component in z direction. I refer to the positive axis x, j refer to the direction of the positive y axis, and k refer to the positive z direction. And in order to calculate the magnitude, we say that the magnitude of that vector is going to equal the square root of fx squared plus fy squared plus fz squared. And this one, like you can see, it was written in the bold font, which means that this one is a vector. And sometimes we are going to, if you are going to write it in the italic font, you need to put an arrow at the head of the letter. And this one, it was written in the italic font. That means this one is the magnitude. So I can calculate the magnitude is going to equal the square root of fx squared plus fy squared plus fz squared. So here is the vector and here is the magnitude. And we say that if this one is the vector and this one is the magnitude, I can calculate the unit vector. And the magnitude of the unit vector is 1. So the unit vector equals the vector over its magnitude. And I can divide the vector over its magnitude to have fx over x and fy over f and fz over f. And we know that fx over f is the cosine alpha, fy over f is the cosine beta, and fz over f is the cosine gamma. So cosine alpha represent fx over f, cosine beta represent fy over f, and cosine gamma represent fz over f. And this summarizes what we have studied in the previous slides. Now, if we have more than one vector, here we deal with only one vector. what if I have vector A and vector B in 3D dimension? We used to have two vectors, but it was in 2D. But now we need to sum two vectors in 3D. Of course, if you are not going to use the Cartesian notation, it's going to be very difficult to handle this. But we use the Cartesian notation in order to make the operation very easy. So here I have a vector A. Vector A is AXI plus AYJ plus AZK. And vector B is BXI plus BYJ plus BZK. This one is vector B. It's not always I'm going to have the three components. Sometimes a vector does not have component in Z. Sometimes it doesn't have component in Y. Sometimes it doesn't have component in X. So here is the general situation when you are going to have three components for the vector. So now I have vector A and vector B, and I need to calculate the resultant. The resultant is going to be very easy. I'm going to say that the resultant is equal to vector A plus vector B. And I'm going to say that AXI, I have AXI and I have VXI. I'm going to take I here as a common factor. So the new vector, I'm going to have AX plus BXI. So the component in I for the new vector is going to be AX plus BX. And regarding the I, I'm going to sum AY plus BY. So the component in the Y direction is going to be AI over BI. And regarding the K, the new component is going to be AZ plus BZ. That is why using the Cartesian vectors is very easy. And if you want to get the subtract, which means that you want to subtract A and B, you are going to say that R prime is going to equal A minus B. The only difference is going to be instead of having positive, you are going to have negative. So when we have, now I have only two forces. Maybe I'm going to have three forces, four forces. It doesn't really matter because I'm going to say that the resultant is going to equal the summation of the forces in X. So maybe I'm going to have C. So C is going to be C. C vector is going to equal CXI plus CYJ plus CZK. And in order to calculate the resultants, I'm going to sum all the X components and in I direction or in the positive direction of Z. I'm going to sum the component into Y and followed by J plus the summation of the component in Z. So even if I have three vectors, four vectors, it doesn't really matter because using Cartesian vectors make it very easy for us. So now I'll give the floor for you to if you have any questions regarding what we have mentioned here. Now I'm going to give you three examples to make you relate all the information together. Now, do you have any questions so far before we start the first example? Okay, so let's get with the first example. Example number 1 says that we have a force vector that equal 1.2i minus 1.8j plus 3.6k. And the unit, of course, is kilonewton. And it's required to determine the magnitude for that vector. So I have a vector which was written in the Cartesian notation, and they want us to calculate the magnitude. And also they want to know the unit vector, and they want to know the three coordinate direction angles. They want to know alpha and beta and gamma. So first we need to calculate the magnitude. So if you do remember, the magnitude of a vector is going to equal the square root of fx squared plus fy squared plus fz squared. So here fx represent 1.2 and fy represent minus 1.8. Of course, here if you are going to have the square, it doesn't really matter. and fz represent 3.6. So I'm going to substitute these numbers here in this equation. So the magnitude is going to equal the square root of 1.2 squared here plus, open the bracket, minus 1.8 squared plus 3.6 squared. And the answer came out to be 4.2 kilonewton. Now we managed to calculate the magnitude. So we have a vector and it's required to calculate the magnitude. Now we have the formula for the magnitude. We managed to calculate the magnitude. Now they want to calculate the unit vector. Remember, the unit vector is the vector itself over its magnitude. So the unit vector over the equals the force vectors over its magnitude. I'm going to divide the magnitude over all these three components, like this one. So I already have f. What I will do, I will divide each term over 4.2. So now the unit vector is going to equal the parts over its magnitude. This one over the magnitude, this one over the magnitude, and this one over the magnitude. And if you divide this one over that one, I'm going to have 2 over 7i. If you divide this one here over 4.2, you are going to have minus 3 over 7j. And if you divide this one here over 4.2, you are going to have 6 over 7k. And this one here is the unit vector. And we say that the unit vectors, it doesn't have any units. It's dimensionless. And if you are going to calculate the magnitude of the unit vectors, the answer is going to be 1. Okay, so if you want to check yourself to know whether your unit vector is correct or not, if you calculate the magnitude of this one, the answer should be only 1. And the last required here, they want us to get the angles. And we say that the cosine alpha equal fx over f, this part. We need to calculate the cosine alpha. Cosine beta equal fy over f, this part. A common mistake that people do not include the minus. You have to put the minus. And cosine gamma is going to equal fz over f, this part here. So alpha is going to be cosine inverse of 2 over 7, this one. And the angle came out to be 73.4 degree. And for the beta, in order to calculate the beta, you need to calculate the inverse. So it's going to equal cosine inverse of minus 3 over 7. Like I said, many students forget to include the minus. And if you have done this, the answer is going to be incorrect. And regarding the gamma, is going to equal cosine inverse of 6 over 7, which is this part, and the angle came out to be 31 degree. So now I'm going to give you the opportunity to ask. So in the second example here, we have that force, which is in the scalar notation. We have a force equal 100 pounds. So this one is not a vector. This one is the magnitude of the vector. They want us to express that vector in Cartesian notation. So I have a vector, but I don't have, it's not written or expressed as Cartesian vector. I have only the magnitude of that vector. And they give us the angle here with that plane, and then the angle here with that plane. So 60 is located in the plane of z and x, while 45 is located in the plane of x and y. So this one is like that, and this one is like that. They want us to write this as Cartesian vector. So in order to write anything in Cartesian vector, we are going to say that f vector is going to equal fxi plus fyj plus fzk. And we want to know the value of fx and the value of fy and the value of fz. If you manage to do that, we will be able to express the vector as Cartesian vector. So our job is to calculate fx, fy, and fz. 100 bound here represent only the magnitude of the vector itself. So I need to calculate fx, fy, and fz. In order to do that, I'm going to say that I'm going to assume I have axis z and that axis here. Let's call it z dash, for example. Then I have x and I have x dash. And I'm going to consider this as 2D problem. I'm going to resolve the force into z and z dash. Of course, it's very easy if you recall the previous lecture. The force in z dash is going to equal 100 pound multiplied by cosine 60. And the component in the z is going to equal 100 pound multiplied by sine 60. Now I decompose or resolve the force into z and z dash. This is step number 1. So the component in z is finished. So now I have fz. Fz is 100 pound multiplied by sine 60. Now I need to know the component in x and in the component in y. Of course, the component of z is going to be positive because when I decompose this one here and this one here, this one is going to be positive. And here I have the component in z dash. Here I have z dash and I have the component here. So this one, I'm going to consider it as 2D. I'm going to say that I have only the axis x and axis y. And I have a force here which is equal 100 pound multiplied by cosine 60. I'm going to decompose the force into x and into y. So into x, the force is going to equal 100 pound cosine 60 multiplied by cosine 45. And the component here in y is going to equal 100 cosine 60 multiplied by sine 45 in that direction. Of course, the component in y is going to be minus because this one is the minus direction, and the component in x is going to also be minus because this one is the minus direction. So we want to calculate the express that force in Cartesian vectors. Also, we want to calculate the unit vector. So like I said here, I'm going to say that I'm going to have additional axis. Here he call it f prime or f dash. I call it z dash. It doesn't really matter. So here we decompose the force for z is going to equal 100, like I said, sine 60 pound. So we finish with fz. Now I'm going to have new force. I'm going to call it z dash or f dash. So f dash is going to equal 100 cosine 60. And f dash, I'm going to decompose it into x and into y. So fx is going to equal f dash, which is 100 cosine 60 multiplied by cosine 45. And regarding fy is going to equal f dash, which is 100 cosine 60 multiplied by sine 45. And now I'm going to be able to know the fz and fx and fy, which I want them here and here and here. And I need to know that this one is minus and that one should be minus because they are this one is positive, this one is positive, and this one is minus because this one is the positive direction while this one is the minus direction. So fx is positive and fy is negative. Now here I have f, it should be fxi plus fyj plus fzk. Since I have fx, I will put fx here from here. This one is fx and this one is fy, and I put minus because fy is opposite to the positive y. So here I have minus 35.4. And for the fz, we calculated from the first time, which is 86.6. So now I managed to calculate, I managed to express the force into Cartesian notation. In order to check my work, remember I say that 100 here represent the magnitude. If I want to make sure that my work is correct, I'm going to calculate the magnitude again. So if you calculate the magnitude again, of course, the answer is going to equal 100 pound. If it was any number than 100 pound, that means my work is wrong. So to make sure that my work is correct, here in that problem, he calculates the magnitude again. and it's empty out to be 100, which is the 100 in the beginning of the problem. Also, I will be able to calculate the unit vector if it's needed. Actually, in the problems, he does not want to calculate the unit vectors. So if it's like just like that, if you put it like that, that means you finish from the problems. But this was very simple problems. Usually, you need to calculate the unit vector. The unit vector is going to equal the f vector over its magnitude. What I will do, I will divide the magnitude over the components. So I'm going to divide this part over 100 and this part over 100 and this part over 100. And this represents the unit vector. Again, if I want to make sure that my work is correct, if I calculate the magnitude for the unit vector, the answer should be only 1. So if you calculate the magnitude of this part, you are going to find it equal 1. So again, I will be able to calculate the alpha and beta and gamma. Alpha equal the cosine inverse of this part. Beta equal the cosine inverse of that part. Don't forget to put the minus. And gamma equal the cosine inverse of that part. So now I have alpha, which is here. I have beta, which is here. And I have gamma, which is here. And now I finish from the example. If you have any question, please ask me. I'm here to make it clear for you. Now let's go to example 3. So in this example, like you can see, we have more than one vector. We have actually two vectors. We have f1 and we have f2. f1 it's written as Cartesian vector because I have j and I have k. So if you haven't noticed here, I don't have I. It's not wrong. It's just it means that I don't have component into x. And like you can see, the vectors here is not in 3D. It's only between z and y. I don't have component here. But like you can see, for f2, the vector is 3D, which means that I'm going to have component in I, in j, and in k. Also, I will be able to know whether the vectors is right or not or wrong. So this one is positive, this one is positive, this one is negative. That means the vector is in that direction. And this one is also positive. That means the vectors is in that direction. So if this one was down, what will happen? That part is going to be negative because the vector, it has component into negative z. And if that vector was here, then all the component is going to be positive. And if it was here, but it was down, then the z direction, this part is going to be negative. So if the vector is located on the top, the z part, the k, is going to be positive. If it's located down, this one is going to be negative. Regarding the k, if it was on the right side, it's going to be positive. If it was in the left side, it's going to be negative. And regarding the I, if it was in that part, the vector, if it was located in that part, is going to be positive. If it was located in the other part, is going to be negative. So easily I can know the equation of the vector. So now I have f1 and I have f2. I need to calculate the resultant. So here he says that determine the magnitude and the coordinate direction angles of the resultant force. So in order to calculate the magnitude of the resultant force, first I need to calculate the resultant force. Then I will be able to calculate the direction of the direction angles. And of course, in order to calculate the direction angles, I need to know the unit vectors. So first, we need to calculate the resultants. Remember, we say that if I have more than one force, I have F1 and F2, I'm going to have the summation in X and the summation in Y and summation in Z. So FR is going to be the summation of the forces. So it's going to equal vector 1 plus vector 2. And I'm going like I just explained previously, I'm going to sum the i's together and the j's together. So here I have the components of the F1 and here the component of F2. Then I'm going to sum the i's together. So here I don't have any I. That means I'm going to put only this I. So for the resultant, I'm going to have plus 50i. Regarding the j, I have j here and I have j there. So I'm going to know the summation between them. This one is positive, this one is negative. That means the resultant for them, the summation for them is going to be minus 40. So here I'm going to have minus 40j. And regarding the j's, I'm going to sum the j's together. Here I have positive 80 and here I have positive 100. That means summation is going to be 180k. So it's very easy. Now I calculate the resultant of the F1 and F2. And also I will be able to know the location of that one. So I'm going to say that the I is positive. So the vector is located here. It's not located there. And the j is negative. That means the vector is located here, not here. And the k is positive. That means it's located up, not down. That means the location is in that quarter. And of course, I will be able to calculate the resultant. Now I have the resultant. I will be able to calculate the magnitude. He asked about the magnitude here. So the magnitude is going to be the square root of fx squared plus fy squared plus fz squared. And the magnitude came out to be 191 pounds. And also they want to calculate the angles here. So in order to calculate the angles, I need to calculate the unit vector first. So the unit vector is the vector itself over its magnitude. So in order to calculate the unit vector for the resultant, I'm going to say that the unit vector for the resultant is going to equal fr over the magnitude of fr. So here I have 50. I will divide it by 191. The same thing here, minus 40 over 191, and so on. Calculate this one, calculate that one. Then I'm going to have the unit vector. Again, if you calculate the magnitude for the unit vector is going to equal 1, like we just mentioned before. Now we need to know the angles. We know that the alpha is going to equal cosine inverse of this part. Beta is going to equal the cosine inverse of that part, and gamma is going to equal the cosine inverse of that part. So I will be able to calculate alpha and beta and gamma. After I finish, I will be able to draw the resultant. Here I have the resultant, I have the angle here, I have the angle here, and have the angle here. Like I said, the resultant, I can know the resultant is going to be located in that quarter here, based on the sign of the unit vectors, I, j, and k. I'm going to stop here. I explained the concept, and again, you need to solve these examples by yourself. It's very important to solve the example by yourselves. If you have any problems, please send me email so that we can have appointment, and I'm going to review your work where you made a mistake or not. It's the only way in order to pass the course. You need to solve by your hands. I've seen many students. I've been here for 4 years. I've seen many students. Those who do not solve the problems by themselves, they are going to fail at the quizzes and the exams. It is a sure thing. You need to solve these examples by yourself. Go back, try to understand the concept, try to understand the examples. After you understand them, write the problem, cover the solution, try to solve the problem by yourself. Okay, this is the only way in order to master the static and dynamics. Okay, so I'm going to stop here. Now, if you have any questions,